Hey everyone, my name is Noah Wood and I'm an application engineer here at HBK, and I'm very excited to have the opportunity to present a little bit about the Electroacoustic Engine API and some custom applications I created in Python. So to give you a brief overview of the presentation, I'll first introduce the EA engine and the Type 3670 DAC that it accompanies. Then I'll discuss the individual apps that I created. I'll give some code examples to give you an idea of what the apps look like behind the scenes. And finally, I have some video demonstrations so you can see how it works in the real world. So, the Type 3670 USB data acquisition system is a USB audio interface with 8 input channels and 2 output channels. It has built-in CCLD and ICP transducer conditioning, meaning you don't need any external conditioning boxes to use our transducers, which is really convenient if you just want to hook up and go. It works as either a standard ASIO or USB audio device, or with the EA Engine API as demonstrated in this talk today. And it supports 96 kHz sampling rate at a 24-bit resolution, so really high quality analysis level files. The EA Engine is an application programming interface, or API, that accompanies the 3670. It uses the .NET framework, meaning it is compatible with a host of languages that support .NET. Today, the ones that I include here are Python, but it also works with MATLAB, Visual Basic, and lots of others. Any language with a .NET package will be able to work with the EA Engine. The engine provides pre-built functions for input and output calibration, wave file recording and playback, output equalization, and a number of other acoustic tests, including things like step sign, log sweep, and random noise. A DSP toolbox is also available, which gives access to a number of useful signal processing functions. And really the core of the EA Engine is that it allows users to create programs that are very specific and optimized to their needs. We've all probably had the experience as engineers of trying to use a program that does everything and tries to do everything, but the specific test we want to run is under a bunch of submenus of a submenu, and settings are in a different submenu, and really the EA Engine allows you to just quickly write something that will be exactly optimized to what you're trying to do. So here's just a visualization of the EA Engine structure. We have the 3670 DAC communicating with the EA Engine, and we're interacting with the API with the .NET framework. So, like any good API, there's a number of resources that are available. We have the code examples published on our HBK World GitHub, including some basic scripts which only implement 1 or 2 functions. The simple GUIs that I'm covering today are also up there, along with some multifunction apps in a variety of languages. Additionally, the EA Engine comes with documentation that covers sort of every function and object and event that the API might offer in sort of the standard language documentation format. There's also a user manuals for the 3670, which covers all the technical details and some of the command line interaction that you can have. So now for sort of the fun stuff, I created 3 custom applications in Python, which allow for some graphical interaction with these EA Engine functions. I used the PyQt5 GUI package for the interface, which is a pretty common and popular Python GUI package, as well as the PythonNet package for the .NET communication. That's Python's built-in .NET package. And I know that .NET may sound a little alien, a little confusing if you haven't worked with it before, but it is really as simple as creating an engine object and then pointing it to your installation path. It just takes a couple lines of code. Each program is about 500 lines of code or below. That may sound like a lot if you're not a programmer by nature, but for those of you who do program or have worked with GUI creation before, you might look at 500 lines and say, oh, well, that's really not too bad. And again, it's a lot of sort of repeated GUI placements, and the scripts have a lot of comments in them that break down exactly what each line is doing and try to make everything as clear as possible if you're not very familiar with Python. So the first app is the setup and calibration app, which implements a channel setup table along with input and output calibration functions. This allows you to activate and deactivate channels and manually update their sensitivity. And it also allows you to run input and output calibration so that channel sensitivity is automatically updated with one of our calibration methods. It also implements graphical and text feedback so the user can follow what's going on with the EA Engine behind the scenes. Second is the Output Equalization app, which allows you to equalize the frequency response of an output device. Output equalization is really useful when we want to play back a WAV file without affecting the signal with an uneven frequency response from our playback device. I'll show in the demonstration later how we can use this to play back a speech signal with an equalized mouth simulator. And of course, this app provides graphical and text feedback. Finally, we have the Play and Record app, which allows us to play and record WAV files, or play and record WAV files at the same time. This is actually the first of the apps that I built, so it probably has the simplest UI, but I think it goes to show how streamlined you can make an interface when you know exactly what you need it to do and don't have to worry about covering every other edge case outside of your test conditions. And one last time, it has the same text and graphical feedback capabilities as the other applications discussed here. So before we get into some code, how exactly do we interact with the EA engine? Well, we follow this scheme of get, set, execute, and plot. In the case of the command line, this looks pretty simple. We have some XML configuration files which control our test settings. So to get and set our test settings, all we need to do is read and modify these configuration files. Then we execute a command in the command line, and that runs our tests. In the plotting phase, we have live text feedback and the result files, but we don't have access to any visual feedback. But for the examples we're discussing today, we use the .NET API. In this case, we have an EA Engine object. In this case, call it myEngine. By calling myEngine.get, we return a settings object, which we can modify and update. After we adjust those test parameters, we use the myEngine.set to update those settings. In the background, this is updating the XML configuration file, but we don't have to go in and do that manually by hand anymore. It's all handled programmatically. Then we call the myEngine.execute with whatever tests we wish to run. And finally, in addition to the text and result files, we now have access to the live data. So we can plot that data, we can process it however we would like to do that. So let's take a look at what the get and set process for input calibration looks like in Python. The first thing we have to do is get the current calibration settings object from the engine. And this is going to return what our current settings are in the form of this object calibration settings. And now that we have that object, we're going to get the user-defined frequency for the reference frequency from the GUI. We just take that off of the front panel and we set the calibration settings.reference frequency to be equal to that new value. Next up, we're going to get the target level in dB from the GUI, and we're going to convert that to Pascal. And that equation is just an inversion of the decibel equation, so the 20 log target over reference. And if you just sort of turn that equation around, you can go from dB to Pascal instead of Pascal to dB. Then we update that reference level and the unit parameters in this calibration settings object. And update the duration. Here we just set it to 5 seconds, but you can update this programmatically some way if you want to have that be user-defined. And now that we've updated all of these locally in the calibration settings object, we're going to set the new calibration settings by passing our calibration settings object to the engine. So now that we've done the get and set, it's time to actually run the test, and we're going to do that in the execute phase. So the first thing I'm going to do is create a string variable that contains the text for the command we want to run. What I actually do in the script is I get the channel number from the front panel and dynamically create a string with that number, but for the simplicity of this presentation, I'm just going to hard code it to channel 1 here. And then we attach 2 event handlers to the function, event handler functions to the engine object. The feedback function is going to handle text feedback, and the time data recorded function is going to handle our graphing. These functions are defined elsewhere, and we're going to see what they look like on the next slide. Then it's as simple as executing the command. After that, we're going to disconnect the event handlers from the engine. That's just a general housekeeping thing that's going to keep our code clean and our objects sort of uncluttered. So, event handlers may sound a little scary at first, but in reality, they're not too bad. All these functions are going to do is unpack the data passed to them in the args variable by the EA engine. In the case of text feedback, we simply get the text message out of the args variable and then print it to the text box called win.textFeedback that we defined on the GUI. For the graphical feedback, we check that there is data to be graphed, first of all, and then we unpack it. And once we have that data in these two variables, x1 and y1, we simply set that data on the graph that we have on the front panel. All in all, it's pretty simple. You're not going to have to break your back learning how to handle events, and it's not as scary as event handlers may sound. And now you might be saying to yourself, okay, this is great and all, but I really don't know anything about GUIs, or I don't really want to spend all this time making something custom, and I'm not really interested in that. Well, I hear you, I get it. It may seem a little daunting, but there's a few things that I'll note for you. Firstly, GUI creation is really, really repetitive. Once you know how to make and place an object, you're just going to be making and placing however many objects you need. And it's not that bad. Once you know that pattern, it becomes really to implement whatever changes you need. And secondly, there are actually GUI designers out there, like Qt Designer, for example, that you just sort of drag and drop whatever buttons and text box you want into your window, and it handles all of the code in the background. And they make it really convenient to set these sort of things up. And lastly, probably the most importantly, you do not need to make a GUI to work with the EA engine. Every test that I'm going to show you here, this can be done with a script that's like no more than 10 lines long. And for example, here is the script for input calibration. So we have all of the parameters we're just defining programmatically instead of setting something up on the front panel to then take and include. By hard coding these, like I said, it's less than 10 lines, and you can always go into your script editor and just modify these parameters directly as your way of updating them. And I think this really goes back to one of the strengths of an API like the EA engine is whatever you need it to do, it can do at whatever complexity you need. So now for some fun stuff. We actually get to see these apps in action that I made. So this is just a quick overview of the setup I was using. I have one of our microphones, I believe it was a 4189, first set up in one of our calibrators, and then after I calibrated the mic, I moved it over to the Type 4227 artificial mouth that we offer. It's a playback device that's designed to mimic human voice field and adheres to all those technical standards on speech playback. So we'll go through what the process of it is to set up calibrated equalized speech out of the 4227. So firstly is setup and calibration. The first step, starting the app, is as simple as any other Python script, simply by calling its name in the command line. You can also open the scripts from the editor you use, but once it's open, we can calibrate the microphone on channel 2. And it's as simple as pressing calibrate input. And we get a nice visual feedback of what's going on. And once that finishes, we can actually see the text feedback that the sensitivity is updated. It doesn't show up so well on the table there because it's actually the same sensitivity as before, but hey, at least we're being consistent. And right now, I think off camera, I'm moving the microphone over to the mounting point on the 4227. And then when that's done, I'm going to calibrate the mouth. And you'll be able to see the same waveform, but it's going to be a little noisier, a little dirtier, because I was in a noisier environment than outside of the calibrator. It was a noisy office, and because my target level was only 80 dB, and I didn't want to annoy my office mates too much, so you can see that it's not nearly as clean of a signal, but we're still going to get pretty appropriate sensitivity out of the other side. And once we get the sensitivity of the output channel, it updates automatically in the table. This app, it also allows you to manually modify the sensitivities, and you can activate and deactivate channels behind the scenes, which is also really good. Next up is output equalization. So starting the app is the same process as before. You just call its name in the command line. Once the app is open, we can see that it displays the current equalization files that are being used on output channel 1 and output channel 2. We can go in and we can actually select a different equalization file that was already generated, or remove the equalization entirely. This is really useful if you have two different outputs that you're hooking up and you equalize them both, but you don't want to re-equalize each time. But here we'll just run a new equalization. and you can see our signal sweep up there in frequency. And basically what is happening here is the EA engine is going to use the relative loudness of the sweep at each frequency, and it's going to create an inverse filter of that, which is going to flatten out all of those differences in the frequency response so that we have an ideally pretty flat frequency response of our speaker. And finally, now that we've calibrated, now that we've equalized, it's time to play back a speech signal. We have some wonderful laptop recorded microphone sound with this one, but we can select whatever WAV file we want to play back. In this case, it's samplespeech.wav, which is just a short recording of my voice. And once we select our input and output channels and everything, and the other settings, we're just going to play back the WAV file.
Test recording.
And then you have that speech which is also equalized, and it's calibrated so it's at exactly the level you want it to be. So I think hopefully you can see just how much opportunity there is in the EA engine to sort of customize to exactly what your needs are. I really hope you enjoyed this presentation and the demonstrations, and I thank you for attending. And if you have any questions, feel free to ask them now or shoot me an email later. Thank you.